Welcome back to the class. So in today's lecture we will further continue on finding properties and applying those properties to find work done. So in this question we have, you can read this question. So from an initial state where pressure is P1 and temperature is T1, the volume is V1. Water vapor contained in the piston cylinder assembly undergoes each of the following processes. Process 1, pressure, constant temperature, P2 equals P1, 2P1. Then constant volume process, then again a constant pressure process. On a PV diagram, sketch each process. So if we draw a PV diagram over here, so first we have to draw the dome, and then we have to draw a line of constant temperature. So now process 1 to 2 is increase in pressure, constant temperature, P2 is equals to P1. So we have to select an initial position of P1 T1. Let's select that position in the superheated region. Initial position is in the superheated region. Now we have to have a constant temperature process, which means that we need to have this on the line of constant temperature. And the pressure 2 is greater than P1, which means that we have to go towards the left hand side. So here, so this is 1, this is 2. So this is the line of constant temperature. Then we have a constant volume process in which pressure is 2 times P1. So this again is a vertical line. So pressure is 2 times P1. And this point 2 and point 3 would be at the same height because both pressures are equal. Then 1 to 4, constant pressure, V4 equals 2V1. So a constant pressure process would be a horizontal line to volume 4 such that this distance, volume 1 distance, equals the other distance. Then constant temperature, V5 equals 2V1. So V5 equals 2V1 would be a process going towards the right hand side, which will be on this line. and the volume of V5 would be equals to volume of V4. Now we have to draw the work done. Work done for each of the processes would be the area below the process. So 1 to 2 is given by this. 1 to 3 there is no work done because there is no change in volume. Then work done from process V4 to V1 would be the area below it. Now moving to the next question. So in this question we have 3 kg of refrigerant R22 which undergoes a process for which pressure specific volume is given by this equation. So this is a polytropic process because it satisfies this equation. Now the initial state of refrigerant R22 is 12 bar and 60 degrees Celsius. So we know P1, we know T1, and the final pressure we also know P2. So kinetic and potential energies are negligible. Determine work done in kilojoule. So we know the initial pressure and temperature. We know the final pressure. And we have to find the work done. So we can find initial volume from table A9 using the pressure and temperature. So from table A9 we find out that the initial specific volume is so if we apply the polytropic equation, we get the final specific volume. The only unknown in this equation is the final specific volume. And then we apply this to the work done equation of a polytropic process. So we have separated the volume into the specific volume and we get this work done. So always remember that once you are applying this formula, you have to have pressure in Newton per meter square. So they had given us the pressure in bar. So you convert bar into Newton per meter square by multiplying it by 10 raised to power 5. And then you divide the entire answer by 10 raised to power 3 to get the answer in kilojoule. So now moving to the next part is to apply the energy balance using property tables. So This is the energy balance in which there is no change in kinetic energy and then there is no change in potential energy. That is why we have on the left hand side only the internal energy terms. Now this is capital U2 minus U1. So this capital U2 equals M into specific U2 minus U1. So this small U2 minus U1 has units of kilojoule per kg. Now this small U2 has unit kilojoule per kg. Now this formula, case 1, is for a single phase of water. It can be vapor or liquid. Now case 2 is in which state number 2 has two phases. If a state number 2 has two phases, their energy can be divided into two components due to liquid and due to vapor. So state 2 means that in the mixed vapor region, this is state 2. So this state 2 is due to two components, due to liquid and due to gas. So how do we find state 2? So all the properties in the saturated liquid line are called UF. All the properties on the saturated vapor line are called UG. So you multiply the mass of liquid with UF plus mass of vapor into UG to get the specific internal energy in the mixed vapor region. And the last part is that if we have two separate masses of water that mix to form a total mass of water. So two separate masses of water means that we would multiply mass 1 with its specific internal energy, and then we add to it mass with its specific internal energy. Next comes specific heat and CV and CP. So specific heat CV is the energy per unit mass per unit volume, keeping volume as constant. CP is energy per unit mass per unit temperature with pressure equals constant. So if we have internal energy as a function of temperature and specific volume, so if we take derivative of that internal energy with respect to temperature, keeping volume constant, that becomes CV. If we take the derivative of enthalpy, keeping pressure constant, that thing becomes CP. The ratio of Cp over Cp is called specific heat ratio. For air, the value of K equals 1.4. For water, the value of K equals 1. For water, this value is 1 because the Cp and Cv values are equal. For water, Cp equals Cv. Now evaluating properties for liquids and solids. So finding specific volume. So if we draw this line, so basically to find any property in the liquid or in the gas region, we need two properties. Let's say we need temperature and pressure. However, in the liquid region, the properties don't change much. What does it mean? It means that, so for a pressure, let's say this pressure, the pressure on this line and this line, it changes very little. In the liquid region, the volume of it changes very little. So on this line, for the same pressure, the specific volume changes very little. However, in the superheated region, for the same pressure, the specific volume changes a lot. So water in liquid state is incompressible. The properties of it change very little. So if you want to know the specific volume of water, its volume over here is approximately equals to the saturated liquid region. So Vf means saturated liquid, Uf means internal energy at saturated liquid, Hf means enthalpy at the saturated liquid. To summarize, that if we want to find properties in the compressed liquid region, we can approximate them to properties of saturated liquid. Now the previous slide was about liquid. Now we move on to incompressible substance model. So incompressible again means liquid. In the previous slide we did the approximation for liquid properties. Now we are trying to develop a model. So a model is a set of equations for a liquid. So Cv, if few slides before we found that Cv equals du over dt keeping volume constant. So in an incompressible substance, the volume is automatically constant. So that equation simplifies to this first equation, that Cv equals du over dt, and the V is automatically a constant. Next is enthalpy. The enthalpy equation for enthalpy is U plus PV, where U is a function of temperature. For incompressible substance, Cp equals Cv. This I already shared that for water the value of Cp equals Cv. Now if we integrate this equation and this equation, we get the last two equations, that change in internal energy equals specific heat into T2 minus T1. This equation we already know that if you have to find the change in internal energy of water, what do? You multiply specific heat with change in temperature. Next, change in enthalpy. If we integrate the second equation, we get, so ut, the integral of this is this, and the integral of PV. So V is a constant for incompressible substance, so V into change in pressure. So this is a model. These are the set of equations that you can use for an incompressible substance like water. So to find internal energy, you can use this. To find enthalpy, you can use this. The alternative way is to use the tables. Then equations for a gas. So if we know the pressure, volume, temperature of different gases, and we take this ratio PV divided by T. If we take this ratio of all the gases and we plot them, on y-axis PV over T and on the x-axis it is P. If we take the ratios of all these gases and plot them, what we would find is that, so those ratios we would plot 1 point, second point, third point. If we extend all those lines, they would intersect on this R bar. All these lines would intersect the y-axis on universal gas constant. So this is how the universal gas constant arrived, that the scientists did experiments. They found pressure, volume and temperature for different gases. They plotted that ratio with respect to pressure, and they found that all the gases intersect the y-axis on the universal gas constant. Now the ideal gas model. So PV equals RT is the one of the equations for an ideal gas model. This equation you are already familiar with. So this R is basically R bar divided by molar mass. So this R bar is 8.314 kilojoule per kilomole Kelvin divided by molar mass. The internal energy is a function of temperature, and the enthalpy is, so enthalpy basically is U plus PV. But for an ideal gas, we know that PV equals RT. So instead we have, for an ideal gas, U plus RT. So U is a function of temperature and RT has temperature inside it as well. So in today's class, we've learned ideal gas model, and we also learned the incompressible substance model. So I hope you learned that before this we were using the tables to find different properties, but now that we have the model for finding incompressible properties as well as gas properties.